Good. Let's get started. And okay, so my name is Chris Thalinger. I work for Twitter. I live in Hawaii, so I'm back here now in Europe. It was good this morning. It's raining now, but that's European weather. So first of all, who has a Twitter account in here? Yeah, that's pretty good. Okay, so Twitter has a small VM team. We have like a VM team of 4 people. There are 3 GC engineers. Most of the time they're doing some support work and making sure that our microservices run fine. And then there's 1 compiler engineer, and this is me. So and if you're going to tweet about this talk, which I would encourage you to do, I saw some tweets in my hotel room earlier from the conference, so I knew what was going on. We have this hashtag for our Twitter VM team, so if you can add that, that would be nice. Okay, so why am I doing this talk? I'm doing a lot of Graal talks, and they all have one goal, and it is to show people the advantages of Graal, and the main purpose is to encourage people to try it out. Okay, so this particular talk is to show people, in this talk I'm not showing you how to save money. That would be my other talk. But I want you to see in this talk how easy it is to just download a JDK and turn it on and try it out, so that eventually maybe you can save some money, that we all as a community can save bugs, and also potentially to improve Graal. If we run more code with it, we can improve on whatever it does, optimizations and so on. So after my previous talks, people came up to me and they usually ask the same questions. They ask me, so is it safe to use? Because it's an experimental research development project still, right? So is it safe to use? How do I use it? Where do I get it? And exactly these questions we're going to answer today. Sometimes they send me emails when they've actually tried it, and they are mostly complaining about benchmark numbers. So they were using the benchmark they were using for 10 years, right? And they were running it, and it didn't turn out as well as they would like it to. And they most of the times they say it sucks. And the reason for that is they don't understand the properties of Graal. It's kind of you have to know what it is, how it works, to be able to benchmark it properly, for example. Okay. So this is all stuff we're going to talk about today. If you want to know more about the saving money part, there's this other talk I'm doing. It's called Twitter's Quest for Holy Graal Runtime. And there are a bunch of, I think there are at least 3 or 4 recordings of that talk on YouTube. So you can watch it on YouTube. It basically looks like this. It's me giving a talk. So what is Graal? Who knows what a JIT compiler is? Good, perfect, so I don't have to explain that. So it's a Java virtual machine just-in-time compiler, that's it. Oh, and maybe I should say, because people might be confused, because Oracle Labs are overloading the name Graal now, because they rebranded their whole strategy to something called Graal VM. Okay, that's not what I'm talking about, because Graal VM has all the truffle substrate VM and the compiler Graal in it. And when I say Graal, I'm only talking about the compiler. So Graal is actively developed by Oracle Labs. There's an official OpenJDK project. The source code lives on GitHub. It uses JVM JIT 243. We'll talk about this a little bit later. It's a compiler interface in HotSpot so that you can plug in Graal and turn it on and use it. And Graal is written in Java. Okay. One of the most important things you should take away from this talk is it's written in Java, because this is the main difference between the existing JIT compilers and Graal, and this is also where people make mistakes. Okay, you guys know what C1 and C2 are? Okay, so I'll quickly say that. So HotSpot, people know what HotSpot is? Yes, the JVM in OpenJDK. So HotSpot has 2 just-in-time compilers. One is called C1, or client compiler. The other one is called C2, or server compiler. And both of them are written in C++. Okay, so this is what you're using today. And Graal would be just another one of these which you can turn on. Okay, so where do I get it? As always, it depends. And this is unfortunately a slight issue right now. And if I give the talk in about a month, I can delete these slides because it has to do with JDK9. So JDK9 has something in it, CHEP 295. It's ahead of time compilation, so it's basically taking Java bytecode or Java classes and compiling it down to native code. And if we go to this CHEP here, we'll see, okay, yeah, it's in release 9, and it's definitely closed and delivered because 9's out for a while now. And if we scroll all the way back to the bottom where it says dependencies, it says it depends on 243, the compiler interface, and then it uses Graal as the code generating backend. So the AOT feature in JDK9 uses Graal. And it also says the project will merge Graal core into the JDK and deliver it in Linux x64 builds. And that's the it depends part. So if you have a JDK9 for Linux x64, you have the AOT feature turned on, and that means one of the modules in JDK9 contains Graal source code. Okay. So if we go back here, and then there is this ticket that would add platform support for Windows and Mac to write out native code so that you could have AOT as well on these platforms. But this is coming in 10. And 10 is coming in what, 3 or 4 days now? Okay, well, that's crazy. Time is running fast. So you need a JDK with JVM CI and AOT, and then this is the case if you run on Linux x64. I think what most people do in data centers and on their servers. So you need something greater equal than JDK9. If you want to do it in Mac and Windows, it's 10, which comes in a few days. So, So these are the URLs where you can grab it, and we'll grab it in a second. So the way I'm doing this talk is it's a little risky, and that's where we are, running down this line of wired Ethernet here. This talk, I'll do all my demos on an Oracle Cloud instance, and I'll fire up this instance now, and it's completely from scratch and fresh, because I like it exciting. And now the real reason is, when you see talks and people do demos, or when I see talks and people do demos, I always ask myself, okay, how many hours did these people spend to make sure the shit works, right? I hope this is not recorded, I say shit. It's crazy, right? I don't want to do this. I want to show you how easy it is to use it. So this, we'll fire up an Oracle Cloud instance right now. And it doesn't even have Java installed. It doesn't even have Git installed. We have to install this shit all while we're doing this talk, so bear with me. There will be a bunch of really awkward pauses when we're waiting for things to download. So bear with me. Okay, here we go. So Oracle Cloud, I'm going to mention this later as well. I'm part of the Oracle Developers Champions program, and through that program, they let me use the Oracle Cloud for free. And so I can show you this stuff. So we are here in, let's call this Vienna. Oops. Oh yeah. And the other thing about this talk is the typing, right? Typing in front of people is always a little unnerving. So we're using this Denza IO one, which has 4 cores, if I remember correctly. Then we have to set up some networking stuff right here, which is not really important. And then we need some SSH keys, which we grab here. Okay, so my key, and paste, and add, and launch, and then we cross fingers. Okay, so here we go. So we're provisioning this instance. I'm just waiting another few seconds to get this public IP address here. The provisioning is pretty fast, but then imaging the thing and waiting for the instance to come up will take a little bit. So in the meantime, we're going back to the slides. And in the meantime, I talk a little bit about me. So who in this room does not speak German? Okay, cool. So, ich bin ursprünglich aus Österreich. Und ich bin aus Oberösterreich, bin in Oberösterreich aufgewachsen, bin in Wien auf TU Wien gegangen und habe dort Informatik studiert. Und jetzt bin ich halt in Amerika und arbeite für Twitter. So, that was that part. So I'm working on JVMs for over 13 years. And back in the day, so at the university, as I just said, I was working on a JVM implementation called Cacao. You know, it back in the day was using GNU GlassPath, and so we were all the people working on GNU GlassPath, the Wild West against, you know, the big bad guys, Sun Microsystems with the closed source Java. And then when Sun open sourced Java in 2007-8, you know, suddenly they became more friendly, and I thought, okay, yeah, this is a cool company. And then in 2009, I started working for Sun. And it's very interesting because I was still in Austria working for Sun Microsystems, and the office they had was just over there in that building complex. No, it's the same building complex we're in right now. So that's where I started working at Sun. And then in, I don't know, a couple of years later, Oracle acquired Sun. We all know that. So the biggest three things I worked on while I was in the HotSpot compiler team at Sun or Oracle was JSR 292, which is basically invoke dynamic and method handles and all this stuff. So I implemented a lot of this. I wrote all the compiler support. I wrote a little bit of interpreter support. I wrote a lot of the core library, Lambda 4 method handle implementation. So that was a big project. It was interesting. So if it doesn't really work well, you could blame me, but don't do that, because in the meantime, a lot of other people touch the code, so I'm not sure. It's not my fault. Then I worked on JEP 243. We already heard that earlier. And that came into the JDK 9, and I wanted this in because I wanted to be able to have the ability to use an Oracle JDK, an official build, and then use Graal and plug it in and turn it on, right? And then after that, I was working on ahead of time compilation, and so there were two reasons why we did that. Number one was for many years, Sun and Oracle customers were asking for that feature. They said, "Oh, we want to AOT compile stuff." And the second reason was we wanted the ability to AOT compile Graal or any other component of the JVM that is written in Java to AOT compile it. Good, so we have that, we can do it. If I would have more time for this talk, I could show you how to AOT compile Graal and run with that. But as it is, I don't even have enough time to show you all the demos I have. And now I'm working for the Twitter VM team. Let me quickly see if this is up or not. Yes, it is. Okay, good. So what we want is, as I said, there's nothing installed on that machine. So we log in twice because we're going to compare C2 and Graal later. So we need two here. I also told you we don't even have Git, so we need that. I'm installing Git. I'm sorry, my nose is a little running today, so copy this guy. And now could be one of these awkward pauses. No, it's not, because it's downloading fast. Excellent. Perfect. So unzipping. Typing is important. Here we go. Okay. Then we go here. We set Java home, because some of the stuff we're going to do later will need Java home. Then we put it on the path, because we will run it all the time. Here we go. Oh, typing's really bad today. Okay, so here we go. No, I fucked it up. Did I? Yes, I did. How about now? Perfect. Better. All right. Good. So we have Java 9 now. one thing that Java has is it has a command line option now called list modules, and lists the modules of all the modules that Java 9 has. And the one we're looking for now is the AOT module. So there's a jdk.aot module because we are running on Linux x64. If you do this on the Mac, you won't see that module. So there's another, yes, there's another option called describe module. And we're going to describe the AOT module. And it needs 2 of these. Here we go. So it has a bunch of contains and requires, and for example, it requires a module called jdk.internal.vm.ci. That's the JVM CI I was talking about earlier. It's the compiler interface that Graal uses then. And it also requires jdk.internal.vm.compiler, and that module contains the Graal source code. So if you have these 2 modules, and since JDK AOT requires them, they are there, we're good. So we could technically, take this and then say this, and we would see them, right? Okay, these are the 2 modules we need, and if we have them, we can turn on Graal and run. So let me quickly over here set Java home as well, and the path to. Good. Okay, going back to the slides. Yeah, okay, we'll skip that. So how do I use it? Get a JDK with JVM CI and AOT. Yes, we checked that we have that. We verified that we have both modules, and then just turn it on. That's really it. There's nothing else to it. Okay, so let me show you how to use it. So let me set a few more things here. We're going to use something called Java tool options. It's a very useful environment variable that picks up, that's being picked up automatically by the Java launcher. And one thing we do is we use the parallel GC by default because we're looking at some GC output later. It's a little easier to read. And we set a pretty small heap size. And we do this, that's wrong. We do this to set a level playing field for both the compilers, because C2, the other way around, Graal allocates some memory. We'll talk about this more later, and so we start with the same heap size as the maximum, and it's pretty small, so just apples and apples comparison. So we set that. We copy that over here. And now we are going to the CHEPs. And then there's CHEP 243 somewhere down here. CHEP 243, here we go. And if you scroll all the way down, it will tell you how to turn it on. Okay, here it is. So you unlock experimental VM options because JVM CI itself is still experimental. Then you tell it, enable JVM CI. So you just enable the interface in the VM. That doesn't automatically turn on Graal as the compiler. It just gives you access to the interface, okay? And then if you say use JVM CI compiler, it replaces C2 with Graal, okay? And then this one is not really important because we don't have to name the compiler because there's only one, so it will pick that automatically. So we just grab these 3, stick it in here, and here we go. Okay. So if we do a -java version, this will happen. It says, we picked up all these options, and here's the output. So nothing really happened, right? So what's going on? Did we do anything wrong, or what's going on? No, we didn't do anything wrong. It's just the way it works is JVM CI itself and Graal are lazily initialized, okay? So if you're not doing anything, nothing's going to happen. There is a command line option, print flags final, and we're looking for JVM CI flags. And always do a -version because otherwise you get all the crap at the bottom. So there are a bunch of JVM CI flags here. One is, enable JVM CI. That's true because we turned it on. But the one I'm looking for is JVM CI print properties. So I want that. Here we go. It's a very long list of properties, and properties in the sense of Java properties, because JVM CI is Java and Graal is Java, so all the options you pass into these two are actually Java properties, so dash capital D, you know how it works. Okay, so there's a pretty short list of JVM CI properties up here, and then the rest is all Graal, okay? We're looking for this one, the init timer one, and then we just do capital D, init timer, we have to say true, Java property, so on. So here we go. Okay, nothing happened, right? Because if we look at the compilations that are happening, so do people know what tier compilation is? Oh, just 1, 2, 3.5. So tier compilation means, I told you earlier about C1 and C2. And so the way the VM executes Java bytecode is, first it interprets code, right? It interprets it a little bit until it gets a little bit hot, and then it compiles it with a tier level, from 1 to 3, and then eventually that's C1, and then eventually we'll compile it with the tier 4 compiler, which is C2 in the default setup. So tier 1, 2, 3, that's this column. The third column is the tier level of the compilation. So 1, 2, 3 are all C1 in different levels of profiling information, and 4 would be C2 or Graal, but there isn't no tier 4 level compilation going on. So we're not running enough code. Code doesn't get hot enough to actually schedule a compilation, and so that's why JVM CI or Graal is not even initialized. So we have to run a little bit more to do this, and for that we download the Scala da Capo benchmark, because we're going to use that later, hopefully, if we get there, to run some benchmarks. So here we go. This might be our first awkward pause. No, it's not. Great. Loved it. I had a really awkward pause in Ukraine at that point. Downloading with 2 megabytes per second. That was long. So, okay, going back to this one. Scala. Here we go. So if we do a Scala-L, it lists all the benchmarks that the benchmark has. And then we see, okay, there's something going on. So all this output here is from this init timer thingy. And we see, okay, JVM CI is kind of initialized, but it doesn't look like it finishes. So what's happening is it would take too long to initialize JVM CI and Graal. And before it's done, the command I executed exits. So we have to run a little bit more than that. And so we are doing a small run of Aurora. Here we go. Okay, this looks much better. Okay, the benchmark's running now. You know, finish a couple seconds. So we initialized JVM CI here. It took like 78 milliseconds. Then it does this compiler configuration factory thingy where it selects a compiler, and we only have one, so that will be Graal. And so then we initialize this HotSpot Graal runtime class. And then the rest is then initializing all of Graal and the backend for our architecture and so on. And then in the benchmark, we are using Graal. So now we're really using it, and I can, over here, let me copy this guy. So if we run it here with C2, it will be slightly faster, like 4.7. Okay, well, here we go. So 4.7 millisecond, 4.7 seconds versus 5.1 seconds. So this has to do with Graal compilations and all that stuff, which I'll go into more detail later. Okay, going back here. So now we have to talk about bootstrapping, because the difference in time we just saw has mostly to do with bootstrapping. So Graal is just another Java application in your JVM, right? It's written in Java, so it loads Java classes. When you start up your VM, it has Java methods, right? Because it's written in Java. And these methods, Graal's own methods, at some point need to be compiled, because they're getting hot when they do work, okay? And that's exactly what bootstrapping is, right? It's this meta-circular approach. You run the VM, and you yourself, you're a Java application, and you get hot, and then you get interpreted, and you compile yourself, but you're the compiler, so you have to compile yourself. That's bootstrapping. All right. So let me show you a little bit more about bootstrapping. You can do an explicit bootstrap. You can tell JVM CI, oh, please bootstrap yourself. That will look like this. So every dot is 100 compilations. So we wait a little bit. And here we go. So we compiled about 2,500 methods, and it took 10 seconds to do that. Okay, now people will think, okay, yeah, that's not really good. I don't want to do this all the time, right? I don't want to wait 10 seconds to do this. It's even worse if I turn off tiered compilation. Because if I turn off tiered compilation, we don't have C1. We only have Graal now. We only interpret, and we have Graal. And so every compilation goes through Graal. It gets much hotter, and all the compilations take way longer. So I didn't do it. I did. Oh, yes. I'm very sorry. Minus. Here we go. So this will take, you can already see by how fast the dot shows up. This will take 27 seconds or something like this. So no one wants to wait that long, right? You cannot run a command line option and then wait 10 seconds for that to show up, right? But this is not really what you're supposed to do. This flag, we sometimes it's useful to use it in certain benchmark situations. It might be useful to bootstrap Graal explicitly, but most of the time you do it implicitly. As you saw earlier with the, have I deleted it? Yes, I did. But you remember the benchmark ran in about 5.1 seconds versus 4.7. Like it's not 10 seconds, right? So the bootstrap can either happen as I do it here explicitly or implicit. Like it just compiles it in the background when it needs to compile whatever it needs to compile. And so let me show you that. What are we running for that? Maybe this. Let's run that. Then print all the compilations and grep for Graal. Okay, here we go. So these are all the Graal methods we are compiling when we run that benchmark. And this is only the compiler, right? What happens is you run the benchmark methods need to be compiled, and all these, that's really a lot, are compiled as well while you're doing this, okay? But it's running in the background. It's running on other CPUs you're not using, so it's not that it doesn't really show up on the wall clock time. One thing you will also notice is in that third column here, it's always 1. And there's a flag in Graal. Where is it? Here. Come on. There's a flag called C1 only. It's called compile Graal with C1 only. And tier 1 is plain C1 compilation without profiling code to actually profile, to collect profiling data. And the reason it's set up this way is because we want compilations for Graal methods to be as quickly as possible, because we need the compiler. We need the compiler for our own application. So that's why it's set up this way. We could change this and set it to false, and then Graal eventually would compile itself as well, but it would take a little bit longer. You might get better code if you're anticipating that you're compiling a lot of methods late in your run, whatever you're running. It might make sense. Most of the time, it doesn't matter. All right. So that's bootstrapping. Let me quickly talk about this again. So bootstrapping compiles a lot of methods. So in the tier case, it's at least 2,500, and in the non-tiered, it's even more. It's like more 5,000 methods, and that's eventually what you actually compile when you do an implicit, I call it implicit bootstrap. You can either do it upfront or during runtime. That's the explicit versus implicit one. And by default, on demand, Graal gets only compiled by C1. Okay, I have to take this one out. It's really a bug, but don't worry about this now. Okay, very important, Java heap usage. So Graal is, exactly, it's written in Java. That's the main difference between C2 and Graal, is every compilation that you do with Graal, it uses Java heap memory, right? Even possibly Graal methods itself will be compiled with Graal and it will use Java heap memory. So if we set that flag to false, then this will happen. So most people tune their heap sizes to exactly how much they need, right? We at Twitter, we do the same, right? We don't want to waste any memory, so we tune our heap sizes to exactly how much we need, maybe 1 megabyte more because, but what happens if suddenly a compilation comes in and needs 200 megs? Yeah, that's a problem. So this is something to keep in mind, that you will see that memory usage on the Java heap. It will be used either way, because all that memory, the compiler builds up graphs and does optimizations and stuff. So it needs that memory. C2 needs that memory as well, but it allocates it with malloc on the native heap. So in a cloud world, where you have your cloud instance and then you have, I don't know, I'm making up numbers here, I don't know, you have 2 gigabytes of cloud instance memory. And you give your VM 1.5 gig of that memory, I don't know what. C2 will use native memory there, like as much as it can get to compile methods. You could technically, if you run with Graal, you could give your VM more memory, increase your heap size, and then you won't have a problem. But remember, the same memory will be used either way, just in different places. All right. So let's look at this in a small demo. Okay. So we're logging GC here, and we run this one again because it's useful for what I want to show you. Okay, here we go. It's a very compute intense benchmark, so it's not allocating a lot of memory, and it's already done. There you go. And if I do this one, and let me run 3 iterations here, you will see there are GCs happening during the benchmark run. Right on the left, we see, okay, these are system GC ones. They are explicitly GC. The benchmark harness does these to clean up the heap before it starts the benchmark run. We have them over here as well. Here, but then we have these GCs in here, and these are because we're compiling stuff, right? We're compiling the benchmark methods and the core library methods, and this uses memory. These are the explicit ones again. Then we have one in this benchmark run. We have one GC happening, and then in the last one, there's no GC happening anymore. It's because at that point in time, and it's only like 12, 15 seconds of runtime, all the compilations are done, right? All of your, I don't know how many people ever looked at when compilations are happening, but it's in the very beginning of whatever you run. If you run a small thing, I know it's not exactly true, but the majority of your methods, let's put it this way, is going to be compiled in your first 1 or 2 minutes. Okay, so remember this. Going back to here. So what have we learned? Number one, Graal uses Java heap memory. That's the number one thing you have to take away. If you want to use it and you think you would run out of memory, then you have to do something about it. At Twitter, we run our most important services for about 8 months now. In production, 100% in production, run on Graal. And we never had an issue with an out-of-memory situation. It's because our services, our microservices, start up, and all the compilations are happening in the very beginning. but our service is not even ready to accept requests at that point in time. So it's not even using all the memory, right? It starts up, it needs to connect to other microservices, and then it probably warms up itself a little bit. At that point, you're not even using all of your heap. So this is, as in my experience, this is not a problem, but it might. I'm just pointing it out that it could be a problem. And memory is being used anyway, either malloc or Java heap, right? Okay. How much time do I have left? 14 minutes. Okay, cool. So what I'm going to do is I want to show you two more things. I want to show you the production demo. And for this one, I'm going to unset this. I want to download something. It's called Finatra. So Finatra is a framework that Twitter open sourced. It's basically something that we use to build our microservices on top. Here it is, Twitter Finatra. It's a lightweight framework to build fast, testable Scala applications, blah, blah, blah. I don't know what it is, but we use it all the time. Okay, so we're going to clone this guy. And here we go. And I have to do this now because building it takes 4 minutes, I think, because it's Scala, right? We all love Scala C. It's amazing. Here's the part where what I said earlier about setting up your system and shit. This does not build with JDK9, so I have to add something. It's all in my speaker notes in here because otherwise I would forget. So we have to edit this file here, and then exactly like this. And then on top of it, I have to set the trust store. Don't ask me why. So I haven't figured it out, and even if I would, I wouldn't, set up my instance now to make this work. So I'm just passing this in, and there are a couple of examples in Finatra. Here we go, examples. There's one called Twitter clone. So Twitter clone is a small version of Twitter. Like you can post some tweets and it will store them somewhere, and then you can read them. So it's kind of a production thing. It's the best thing I can show you. That's closest to what we do. I could also show you a benchmark, but that's even worse than this. So I'm showing you that. Okay, so let's run this. I hope it builds. Should. Will take a while. Okay. In the meantime, we're going to build Graal, because the version in Graal, the version in JDK9 of Graal is at least a year old. I think it's a version of December 2016, if I remember correctly. And from the experience that we had at Twitter, it's between December 2016 and April 2017, there were a bunch of Graal improvements that we gained at least 3 or 4% more of performance. So you might want to download Graal yourself, build it yourself. Maybe you want to work on it or improve it, fix a bug, who knows. So I'm going to show you this. We're going to clone Graal from GitHub. Here we go. This guy, Oracle Graal. It grew in size over time because, as I told you earlier with the name overloading, in the very beginning, the Graal repo was only Graal the compiler, but then they decided to merge Truffle in, and then also they open sourced Substrate VM pretty recently. So all of that is in that repo now, which does not clone very fast. Okay, and that would be an awkward long pause. So I'm not sure if we're going to do that. Holy shit. I don't know. What? I don't think it's fine. Do it what? Oh, depth equals 1. Let's see. Much better. Ah, that's good. Thank you. I'll use that in my next version of this talk. Ah, okay. Very good. Okay, cool. I know. But he knows that he told me, but next time I'll be the one who knows. So then we need this tool called MX. It's Oracle Labs. It's basically a script. It's a very big script, but you can use MX for everything, for building Graal, for testing Graal, for everything. Like literally everything everyone ever does with Graal, you can do through the script. I should have used the depth one thingy. Because it's easy for people, if you onboard new people, like a lot of students have been working on Graal at the University of Linz, and then when they bring in new students and they have to explain everybody how to do it, they have the script, and it's much easier for them to do. Okay, here we go. So as I said, there's truffle in it, there's substrate VM in here, but we want the compiler, so we go in here, compiler. I'm going to unset these flags that I set earlier because I'm not exactly sure, and I have to try this, but between the talks I don't have the time to do this. I'm not sure what's going to happen if I compile Graal with Graal, if there's an issue or not, so I'm not doing it now. We set Java home, so we are on JDK 9, and the only thing we have to do now is MX build. That's it. And then it should build, and I hope it does. It'll take a little bit. Okay, here we go. So it's compiling stuff, it's downloading a bunch of dependencies it needs, and then it compiles all the projects they have. Graal, the way it's set up, it's very modular, not in the Java 9 module sense, but they split it up in projects, what they call, and in your IDE, you have all these different projects. There are many of them, like 40 or 50, I can't remember. And MX, the build system makes sure that there are no circular dependencies, makes sure no platform, and I always have to be careful when I say this, that no platform independent code depends on platform dependent code and all these things. So it's a very nice setup, and it's made in a way that people don't make mistakes. This build will fail, and the reason it will fail is because it's building truffle as well. And truffle has, it uses FFI, and since this is there you go, it fails, as I said, because we don't have GCC installed, right? My cloud instance doesn't have anything, so I don't have GCC, and it could be, no, I think we got it. Sometimes it's racing a little bit, and then I don't get what I need. But here we go. There should be a modules directory here. Exactly. And this is our modular jar file. Okay? This modular jar file contains the latest version of Graal. So now we can do mxvm dash version, which is just running Java. Okay? That's really all. And to see what's doing, we can do a -v. And the interesting command line is this one. That's the one that's actually running. And then it's using upgrade module path to upgrade the module in the JDK with that modular jar file. That's how you can override some modules in the JDK. So if we do, what are we running? We are logging class loading. And we run Scala. We run my favorite benchmark again. We run this one. And we grep for Graal again. Here we go. So, no. Same mistake as last time. I have to set this again because we were not running with Graal. Here we go. There it is. Okay, so we see these Graal classes are being loaded from the JRT, which is, I think JRT stands for Java Runtime, if I remember correctly. It's the file system that reads from the modules. And so we're loading from this module that we've seen earlier, right? The JDK internal VM.compiler module. If we do the same through MX, we see, okay, all my Java classes are loaded from our modular jar file. So if you upgrade the module path or you run it through MX, then you run with the latest version of Graal. And we can, let's just do this, run without that logging stuff. Let's just run that benchmark, see if it works. Maybe it's faster, that would be cool. Probably not. Here we go, no it's not. So, but if you wanna, play around with Graal, just clone it from GitHub, load it into your IDE. You saw it's really just an MX build, and then you have your modular jar file, and then everything you have to do is MX VM, or you could throw the upgrade module path command option into your whatever on your command line, or the Java tools options I have. Okay, let's see how we're doing over here. Success, that's good. All right. So let me, yeah. SBT is always screwing up my terminal. Okay, we're back again. We set this again, and now we're trying to run this, and we have to go down here. Wait, no, that's wrong. Finatra examples. Okay, here we go. So number one we have to do is we have to turn this on. No, number one we have to do is we have to add a module, because it's still depending on this Java SE.ee module, so we have to turn that on. Then we turn this on. Then we do examples, Twitter, sir, clone, and then target, yes, that's what's called Scala something. Here we go. Here we need that. And then we need these over here. Where are they? Oh yeah, here. I don't know, don't ask me why you need these, but we need to pass these to make it work. Let's see. Should come up, does some stuff, does some warm-up requests, some post requests, some get requests, and then it's started up. It's ready, okay? So it doesn't really take a long time to start up. Let's run this again through time, and we add a little flag called CI time. I haven't shown you that yet. So what CI time does is, let me copy this real quick. CI time is compiler interface time. It will show us how much time we spent in the compilers basically, how much methods we compiled, and how much time we spent doing this. Okay, sorry, let me run this again. I have to kind of, when it's up, I have to press Control-C so that we can compare it better. Okay, here we go. Let's do the same thing over here. No. Okay, it's done in 4 seconds. All right, okay, here we go. Let's go back up. So it's a short example, right? I mean, all of our services at Twitter and probably the stuff you're running is starting up. It takes longer to start up than 5 seconds. But as I told you, this is kind of the closest thing I have to show you what a production thing looks like. So this started at 36.2-ish, and it was done at 41.4. So that's, what, 5 seconds? And over here, it's 51.5 and up to 57.3. So that's 6 seconds. So it's a little bit slower with Graal than with C2, but it's not a lot, right? We've seen this early with the benchmark as well. It's not 10 seconds, right? And if this is only 5, and if your application starts up in 30 seconds or a minute, the difference will be even less, right? Because the whole overhead we're seeing here is, let me scroll here. the difference we're seeing here is in the number of compilations. And so these are C1 compilations, and we've been doing 3,500 C1 compilations here with C2, with a tiered setup with C2, but we've been doing more than twice as many in the Graal case, right? And it took about twice as much time to do this. The difference is, remember that flag that says compile Graal with C1 only? That's that, right? All the Graal compilations are these additional 6,000 methods. Yeah?
Maybe this is a silly question, but you tell us the whole time that the startup with Graal is only a few seconds more.
Yeah. Oh, what's the benefit of using it?
Yes.
Oh, that would be the other talk. How much time do we have left? Zero time? But it's the last talk, right? It's 42. You need to go to the airport. I can show you. It takes me about 4 minutes to show you another demo. That would answer your question. No, it's a good question. Absolutely, it's a good question. Let me just finish this. So with C2, we compile about 400 methods. Here, over here, we compile about 700. That's the difference between core library methods that get hot because we run Graal. So because we're running Graal, more of the core library methods get hot, and so these will eventually be compiled. Down here, that's the important part. We used about 200% CPU in the C2 case because we were doing, application was running and we were compiling stuff, maybe GCing, who knows. And over here, it's 300. And so that's the additional compilations that were going on. And in the very beginning of your application run, not all of your CPUs will be used. So there will be a bunch of CPUs on the side that are not being used, and you just use these. So the overhead disappears because you have free CPUs. Okay. He had a question, and I have to answer the question. So this is this demo, Scala demo. Let me quickly crank up the heap a little bit. And we set it to 2G, otherwise we get too many GCs. And it's difficult to see, and we log GC, and we run this, and we run a benchmark called factory. And usually I do 3, but I'm doing only 2 now because we're running out of time. And this will take, one iteration takes about 25, 27 seconds. So we just have to wait for that. And then you'll see. And you can also watch the other talk. In the other talk, the Twitter's quest for Holy Grail runtime, I basically show a trillion of graphs explaining to you why Twitter saves so much money by using Graal. It's all about the money saving part. That's why I'm telling you this whole thing. The money saving is a lot of power, yes. Yeah, it's power, and you. No, I can't. No, you don't know. But I'm making up a fictitious company in my other talk to kind of give you an idea how much it can be. Okay, here we go. So that took 25 seconds, 26 seconds to run that benchmark run. And we did about, let me run this here while I talk. We did 49.85. So how much is this? Like 35, 36 GCs roughly. Okay? GC iterations. So and we just wait for, no, this is wrong. This is very wrong. Because we don't use the same heap size. Okay, sorry. All right, here we go. So this should run faster, hopefully. Awkward pause, but 20 seconds awkward pause. A question while we wait for it. You have 30 seconds. Yeah.
Why did you create it in Java? What's the benefit of doing it in Java?
I didn't do it, so it was not my idea. I think we'd have to ask Thomas why he did it, but I think it was more of a proof of concept if it could be done. In my opinion, the biggest advantage that it's written in Java is that it's more accessible. If you look at, I mean, no one's learning C++ at the university anymore these days, right? But basically everyone can write Java. And it's so much easier to load it into your IDE, and it's
always been an idea to re-implement more of the JVM inside Java because you can take advantage of having everything compiled.
yeah, you can. One of the big advantages if you have, there is something called Project Metropolis going on right now, it's not, no one's really working on it yet, but Project Metropolis will replace a bunch of the components in the VM with Java written components. One of the big advantages doing this is you own your own compiler. So all the bugs you have in your compiler, you can fix yourself immediately. But let's come back here. Okay, as you can see, it ran in about 20 seconds. That's pretty good. That's like, what, a 20% improvement in runtime. And one thing you will notice, we only did like 20 GCs. So what's going on here is mainly two things. It's inlining combined with escape analysis. The escape analysis in Graal, the implementation of escape analysis in Graal is better. It's called partial escape analysis. And it's better, and it can eliminate allocations. And this is why we're seeing less GCs over there. When you can eliminate allocations, two things happen. Number one, the obvious one, we don't produce garbage. We don't have to collect as much. But the other one is the code compiled is much tighter, because an allocation takes up a lot of code. You know, you probably either have to allocate it on the TLab or call out to the VM, and then you have to clean out the stuff, you have to fill in the fields. If you can eliminate these allocations and maybe scale and replace them. I'm saying a lot of things right now you might not understand, but that's okay. Your code gets tighter. And if you can eliminate allocations in the compiler graph while you're doing the compilation in the graph gets smaller. And so that means you can inline more. Yeah. This is the whole win. This is why Twitter saves so much money, way more than they pay me, because of this.
Is this what you experienced in production? 20%?
No, not 20. Like the factory benchmark I'm showing here, that's really the best case scenario I've ever seen, but it's good to use it in a talk. So I'm almost done. Summary. Turn it on. Just try it out, right? I mean, you might save something, you might not. It might help you. That would be great. You might find a bug. That would be great. Please file one. Fix it yourself, because I've shown you how to download and build it. But if you file it upstream, that would be cool. Tell me if it works. Tell me if it doesn't work. I'm more than happy to help you out. Tweet me. That's my handle. Tweet me. DM me. Send me an email. I'll tell you what to do. I'll tell you what you're doing wrong. But I've told you so much today. You're not going to make the same mistakes as all the people before you, because you know now. All right. Questions?
I've already seen your first talk, and you mentioned there that Graal VM is much more efficient with Scala than Java. Do we know why?
We do, yes, pretty much. Yeah, that's the answer. It's the way. So two reasons. When you look at the bytecode compiled by Scala C, it's very, very complicated. If you look at Java C compiled code, it's straightforward. And then the other reason is Scala has a more polymorphic nature than Java does. And the way Graal does inlining, it can handle that situation better. That's why yes, it's true. And I should have said it in this talk as well, that with Scala, I'm almost sure that you will see an improvement. With Java, it's like a 50-50 chance if you see or not.
Well, my other question was about, other languages, Kotlin, Clojure.
I haven't had time to try this out. I've done a lot of work with Graal at Oracle with Java, obviously. Now at Twitter, all of our microservices are written in Scala, so it's not. I'm glad they pay me to come here and talk about it. If I go back to Twitter and play around with Kotlin, they probably ask me if I'm a little. So, but I just was in Kiev, right, in Ukraine, and there are a bunch of Kotlin people there. They were very interested, so I might come back to them and talk to them again. Yeah, it would be interesting what other languages do. It depends a lot on, as I said, how polymorphic are they, how bad is their source code compiler, things like this. Any other questions? Yes?
So the main benefit is that it saves money by being a better compiler, which could obviously also have been written in another language, not necessarily Java, right?
Absolutely. Yeah. It's just for us, compiler engineers, it's better for it to be in Java because it's easier to maintain, it's easier to find new people. It would be much easier to use that compiler and teach at the university. All these things, right? It's about building up a community of compiler engineers and people who are interested.
Well, HotSpot apparently takes more than 2 years of training.
Yeah, I don't even want to get started to talk about C2 and how bad it is. So,
Do you think Graal will ever replace the default compiler?
yes, it will. In JDK 10, I think when 10's out, pretty much next week, I'm going to take that one slide out, and then I will put another slide in, because in JDK 10 there will be a chap, forgot the name, I can show it to you, chap 243, it's 370. Experimental-based, Java-based JIT compiler, and it's release 10, and it's status completed because it's not out yet, but that's Graal. So in 9, everything I've shown you today, the reason why you can use Graal in 9 is because I integrated all that stuff. Okay, it's nothing that Oracle ever said it would work. I'm just telling you because I know it does. But in 10, they will officially support it as an experimental compiler. And from that day on, it basically only depends on how fast can we get to a point where it can really replace C2. And that means the more people try it, the more mature it will get in a shorter period of time, because a compiler only gets mature when you throw a lot of code at it. And a company, let's say like Oracle, they do a lot of testing, yes, but they test with the same stuff over and over and over again. What you really want is the crazy shit code that you guys write out, or the people before you who already left, that code, right?
So besides a little bit worse performance, what are downsides of Graal? Still experimental. What parts need to improve?
So I think the biggest problem today is the heap isolation. It's the allocations that are happening on the Java heap, and they are visible. I think that's the biggest problem. You can, if I could go over another hour, no, not an hour, but I could show you. I'd have to do another talk about this, I guess. But you can AOT compile Graal. So there are 2 big issues. Number 1, the bootstrapping, and number 2 is the heap allocations. Number 1, you can AOT compile, and then that's gone. The number 2 with the heap isolation, that's still an unsolved issue. But people are working on it, and we'll find a solution. So a real downside in running with Graal is, that's in my other talk as well, since it's a Java application, it uses about, I think it's like 40 megabyte of old gen memory, because it has state. It has some state, right? It's not a lot. It's 40 megs. People freak out about this sometimes, but it's not growing, right? It has its state, and it will have that state all the time. And then you will use a little bit more of meta space, because you're loading, I don't know how many classes you saw. We compiled like 6,000 of Java methods. So it has to be somewhere in memory. So it's using, I think, between 20, It is noise, but people still freak out. It's about between 20 and 30 megabytes of more metaspace. But you have your SREs, the people who take care of your services or whatever you run, and they monitor closely. And if something slightly goes up, they freak out. I had this all the time at Twitter. Like SREs coming running at me and say, "Oh, it's using 40 megabyte more." I said, "So what? We're saving this much of CPU over here." You mean when it's doing a compilation? That's hard to tell because I tried to basically find this out at one point in time. The issue is the way they operate, and it basically all depends on the optimizations it does and how much it inlines. You know, I was talking earlier about, you know, the doing less GCs. It's like I said, if you can remove allocations in the compiler graph gets smaller. If that happens, you can't compare it. It's not apples to apples anymore. So I tried to turn off as many optimizations as I could, but that's also not really what you want. What I found was it's about the same. So in Java, a node object is usually bigger because it has a header. In C or C++, it's more tight. But what happens is most people run 64-bit VMs with less than 32 gig of heap memory. And so that means they run with compressed oops. And compressed oops, a pointer is only 32-bit long and not 64. So there are a lot of pointers in the compiler graph, because a graph is a lot of pointers. And the pointers are only 32-bit long, so it's a wash. 20 minutes over. Great. Could be a record. But I think people are sick now. Okay, thank you very much.